Just a few words in the beginning. So Stefan Gansinger received his master and PhD degree with distinction in electrical engineering and information technology from Graz University of Technology in Austria in 2008 and 2012, respectively. In 2007, he joined Infineon Technologies Austria in Graz as an analog design engineer. And in this position, Dr. Gansinger is in the role of a principal engineer working in various fields of analog circuit design with a special focus on ultra-low power, low noise, and high-speed design. He holds several patents and publications that cover a broad field of expertise. Furthermore, he specializes on verification methodology for analog circuits, where he gives technical advice within the company. And Mr. Gansinger, it's a great pleasure having you here. Thank you very much for coming, and the stage is yours.
The title of my talk today is Analog Design and Verification for High Parametric Yield. Let's say the buzzword for today is yield or yield loss. What do we mean with that? When we are producing chips or wafers, the production side is of course non-perfect. We have variations, we have instabilities, we have particles in the fab, and all of this influence the quality of our chip. And of course, we do not want to deliver any chips which have a defect or do not work as expected to any customer. And to avoid this, we are testing each IC in production for certain parameters against given specifications. And by yield, we refer to the number of chips, it's typically in percentage, which fulfill all given specifications and can be delivered to a customer. Or in other words, yield loss is the amount of chips which are failing in their specifications and we have to throw them away. And of course, we want to have a very high yield value or a low yield loss value because this is direct cost and of course margin in our sale. When we speak of yield, we can distinguish three different major categories. We have the so-called parametric yield loss, we have a systematic yield loss, and we have a random yield loss. Today, we want to focus on the parametric yield loss. What do I mean with that? So, due to variations within the individual processing steps, which are quite many in a CMOS fabrication, the device parameters like a threshold voltage, for instance, vary. And due to this variation, of course, also the performance parameters of analog circuits vary. And if this variation is too much, we have significant yield loss. And this needs to be avoided. Next to this, there's also systematic yield loss, which is typically given by structures on the wafer. So if you have structures which have so-called low manufacturability, this means there is a probability or a high probability that the production won't work. This is called systematic yield loss. So for instance, if you have dimensions which are really small, you have small distances between devices and similar things. And random yield loss is typically caused by particles which are in the fab. You know already that the fabrication is done in a so-called clean room, where we try to keep the air as clean as possible, but still there are some particles, and these particles might hit our wafer, our chips, and cause defects like shorts or opens. For the latter two, so the systematic yield loss and the random yield loss, we cannot do much in design, but for the parametric yield loss, we can do many things. That's why I want to present this topic today. I want to do this in two major parts. I will start with an overview on this variation. So I will show you what variations we have, what they are causing, and what we can do in analog design against these variations. Typically, we distinguish between so-called global variations and local variations. So I will do this distinction also in my talk today. And the second part is dealing with verification. Of course, we want to make our circuits robust against these variations, but we also want to verify that the robustness already in pre-silicon. So we want to make sure before we go to production that our circuit will have a high yield. Since all of these variations are statistically or a random process, we have to do statistical verification with this respect. With statistical variations, there's quite a well-known technique. This is the so-called Monte Carlo simulation technique. I will show you this, but I will also show that this has quite some limitations, which makes it not really useful for us when we want to verify high yield. There are better, more innovative solutions, and I will show you some of the methods which are available here. You will see that these methods also have some drawbacks, and of course there will be an outlook what would be a nice solution, so what we need from analog design point of view. And at the end, of course, there will be a summary and a takeaway slide. So I tried to summarize the whole content of this presentation in one slide. I will wake you up when I'm there, because if you have this slide, you get the most important messages, what you should learn. I also want to mention that in the slide set, there are much more slides than I'm going to present today. There are more details, and some other interesting stuff. Of course, you will get the slide set. You can have a look on these details. And of course, when you read this and some questions arise, do not hesitate to contact me also after this lecture. So I'm really happy if I can answer some of your questions. Okay, so before I start with the technical content, I want to define, because this is a lecture, and for lecture there is always some exam or a quiz. I want to do this here as well, but please do not take this too seriously now. So if you follow the presentation and look carefully, you will be able to answer the quiz at the end of my presentation. What is this quiz about? So when you work as an analog designer in the industry, one nice thing is that you have to interface many different disciplines. So you have to talk to concept engineering, you have to talk to component verification who verified your chip in the lab. You have to talk to test engineering, which makes sure that the test program is covering all potential failures in the chip, and so on. On the one hand, this is very nice, but on the other hand, yeah, you're always busy and you will get many questions. And sometimes there are questions where you do not have the time right now to answer them, and you do not want to answer them at the moment. And for this, we designers, we invented, so to say, 3 answers, which we are giving to questions we do not want to answer in the moment. Originally, these answers were in German. I tried to translate them into English. Of course, what you can always do is simply choke off the question by answering in German, "Ich weiß nicht," or in English, "I don't know." What is also working is raise another question to distract from the real problem. So in German, we start with "this Problem ist," or in English, "the problem is," and then we speak about something different. Or my favorite one is, the third thing is make things unnecessarily complicated. So for the person who asks, it's impossible to follow. So in German, you start with, "Das kann man nicht so einfach sagen," or in English, "It's impossible to state this simply." And the quiz today is, so these answers are answers who a typically analog designer can give. But since we talk about statistics and statistical verification today, I will ask you at the end of the presentation, what are the answers for an analog designer who knows statistical verification as well? Okay, coming back to the serious part. As said, I want to start with the variations within the CMOS fabrication process. We distinguish between global and local variation. What do we mean with that? For global variation, which is also called process variation, it's just another name, we speak about differences between two individual dies on a wafer, or it could also be differences between individual wafers, so wafer-to-wafer differences, or lot-to-lot differences. A lot is a bunch of wafers which belong somehow together. For instance, a typical global variation is you have one die where all capacitors are smaller than the typical value, and you have another die where all capacitors are larger than the typical value. Sometimes this is also referred to a slow or a fast wafer or similar. So these are called global variations. Local variation is something different. For local variation, we refer to two devices on one die, which are placed in a so-called supersymmetrical environment. This means these two devices, like transistors, are placed next to each other, and the surrounding of each of the devices is equal. So theoretically, we would expect that the device parameters, like a threshold voltage of these two devices, is equal. But you will see, due to local variations or fluctuations, the device parameters will not be the same, and they will have a mismatch. This is why the local variations are also called mismatch. But let's start with the global variations. I tried to find a cross-section of a single transistor, and I put it on the slides. It's on the upper right. If you look to this picture, you clearly see that this doesn't look so nice like we would expect from a simplified textbook. So it's somehow wobbly. There are no real straight lines, so it's not so nice. And by seeing this, it should be already clear that controlling this structure is not an easy task. So we will see a lot of variations within such a single device. When we look to the simplified equation for a transistor in saturation, so the drain current, we see a lot of process constants, so values which are given by the process. So for instance, we have the mobility, which is typically influenced by the doping constant. Then we have, of course, the gate oxide, which is given by the thickness of the gate oxide. Then we have the sizing, which is W and L, so the width and the length. This is influenced mainly by the lithography, so by the optical process. And of course, we have the very important parameter, which is the threshold voltage. And this is influenced by many process steps. So by doping, also by the halo, for instance, or by the lightly doped drain. So when we look to this and also this picture, we are expecting many variations for the devices on the wafer. Of course, we do not allow that these variations are not controlled. So there is, of course, a specification for the individual variations, so what is allowed, and also there is some monitoring. This monitoring is typically done with so-called PCM structures, where PCM stands for Process Control Monitor. These are structures or devices which are placed in the scribe line of the wafer. So we have here small devices, small structures, which can be used for measurement during production test. We are measuring fabrication parameters. So for instance, the resistance of long and narrow lines, which is a monitor how well the metal stack is produced. Also, we have devices in the PCM parameters, like transistors, resistors, and capacitors. And we can do some measurements on these devices. Yes, this sounds nice, and it seems like we have everything under control, but I have to disappoint you, this is not the case. Why not? This is because for the PCM, we distinguish different levels of importance. This means we have three categories. We have so-called wafer acceptance criteria, we have key electrical parameters, and we have other parameters. A wafer acceptance criteria means that if a certain PCM parameter is out of spec, and typically this is a majority decision, this means we have more than one PCM structure, and the majority of this PCM structure has to be out of spec. And if this is the case, the wafer is thrown away. A famous example for this is the saturation current of the transistor. If this is too high, of course, in digital design, this would mean we have an excellent speed because we have a high current, but this poses a reliability risk because due to hot carrier effects, the transistor performance degrade over lifetime. So we have to throw this wafer away to not run into issues here. Contrary to this, we have key electrical parameters. These are parameters which are measured, and when we see that the process drifts away, we do correction measures. So for instance, the sheet resistance of resistors is a typical parameter, which is a key electrical parameter. So this means that the sheet resistance can be out of spec, at least for a short period in time, until we do our correction measures. And the third parameter, what we have, so the other parameters, they are monitored, but there is no control for them. So for instance, in analog design, GDS is a very important parameter. This is monitored in the PCM structure, but there is no control of this. What is also important to know with respect to analog design, device parameters which cannot be measured quickly. So for instance, temperature coefficients or flicker noise constants or similar parameters, they cannot be measured in production tests because it would take much too long. So from this slide, we already see that the PCM parameters do not have a focus on analog circuits because it's simply not possible to do this in production test. This means for us analog designers, we have to make our designs very robust against variations in the fabrication process because they are not really controlled with the focus on analog performance. So to summarize this, our analog circuits must be designed to be robust against these global variations. And be aware that on top of these variations, we have other variations like temperature variation, we have supply variation, and much more. So we really need robust design concepts here. How can we do this? So instead of using analog designs which depend on absolute parameters, like an absolute threshold voltage, for instance, we try to use design concepts which are based on matching rather than on absolute parameters. For illustration, I have an example what I mean with this. And what we should never do is we should never compensate unwanted effects by other effects which are based on different physics. So for instance, we have different types of resistors. So for instance, we have a polyresistor and we have a diffusion resistor. And let's say the polyresistor has a positive temperature coefficient and the diffusion resistor has a negative temperature coefficient. One might have the idea to compensate this by connecting them together, but this will not work because the temperature coefficient of the poly has completely different physics than the one of diffusion, and they are completely uncorrelated. This means for one die, the compensation might work, but due to variations on the other die, it might get even worse. So we are never doing things like this. Of course, what can be done is trimming. Trimming is a measure to define a certain output. So for instance, if we want to have a defined bias current, we can measure it on the tester, and by using a DUC, we adjust the current to a value what we want to have. Yes, this can be done, but typically this is expensive because on the one hand, it requires some time in the test, which is cost. And on the other hand, we need some non-volatile memory, like a flash or a eFuse where we can store the trim result. So trimming is an option, but if it can be avoided, of course, this has a big benefit. As promised, for illustration, what I mean with design based on matching rather than on absolute parameters. If you have the task to design an integrator, and you look to a textbook, you might find a solution like this. So you have an op-amp with the capacitor in the feedback and the resistor at the input. The tau of this circuit is given by the product of R and C. If you need an accurate tau, this design is not a good idea to implement this on silicon, because we have a resistor which is fabricated with different processing steps compared to a capacitor. This means that the sheet resistance will have a variation which is completely uncorrelated to the variation of the capacitor. So we will see a large variation of tau from die to die, depending if we have a large or a small capacitor or resistor. A better way to do this is to use two capacitors instead of a resistor and a capacitor. The advantage of this is, of course, we have to choose the same type, that if this capacitor is larger because of some non-ideals in the processing step, this one is also larger. And in the end, this will cancel out. So this is a design which is based on matching, meaning the matching of these two capacitors. And this is a design which depends on absolute parameters, which is not so nice when we do this on silicon. Of course, some absolute parameters still remain. So for instance, here we need an accurate frequency, but typically frequencies can be generated with a high accuracy on silicon. So this is much better than this one. Speaking of matching of these two capacitors, this brings me to the second topic, which is the local variations. So local variations means we have differences in devices which are, at least theoretically, perfectly equal. I tried to draw a simple layout here. So we have 4 transistors, 2 transistors, maybe cascodes, and 2 PMOS transistors, which can be current sources. If we look to this, there is a mirror axis. So the left side and the right side are perfectly symmetrical. From this, we could expect that the transistor on the left side equals the transistor on the right side. But due to so-called random fluctuations, this isn't the case. There are different effects which influence this behavior. So for instance, we have the diffusion effect, we have the implantation, which is not homogeneous. Then also from lithography, we might have some differences. And there are also stress effects on the silicon. So there is SDI stress, for instance, which is coming from the border of the diffusion to the substrate, which have an influence on the transistor parameters. Or especially for modern technologies where we have short channel transistors, we have to implant in the drain area to reduce the electric field, for instance. And typically such implants have a bad matching. Of course, we want to somehow deal with this in analog design. And of course, there are solutions how to improve this. And I will show you how we can do this and what you can do. I would distinguish two measures. First, we want to avoid unwanted systematic offset. So by accident, although we want to have matching devices, we are introducing unwanted offsets already in the design or in the layout. What do we need to do here? Of course, we need to ensure the symmetry already in the design. And for the layout, we have to consider layout effects. I have some illustrations on this as well. And also for this, I will show you more details. We have to use so-called unit devices. So this is the first measure we are going to do is, so we are reducing unwanted systematic offset. What remains is the random variations caused by fluctuations. This can be reduced by what I call smartly sized devices. So you will see that the area of the device will have an influence on the variations. And if we use this with respect to analog performance parameters, we can reduce the standard deviation, so the variation of the device parameters. Of course, I will also have an example on this so that you understand this a little bit better. Regarding the systematic offset with respect to layout effects. So there are many effects caused by non-optimal layout. One very famous is the so-called well implant proximity effect or N-well proximity effect. What is this? So let's assume we have two transistors like this, and they should have a perfect matching. But next to the right transistor, there is an N-well. So this transistor sees a different surrounding than this one. And typically, an N-well is fabricated using implants, and these implants might not only hit the N-well, but also the transistor which is closer to this N-well. And these implants will cause a threshold shift of this transistor. So due to this N-well, this transistor has a different threshold than this one. And of course, this causes a systematic offset or an unwanted systematic offset between those two transistors. Of course, there are measurements on this. I've cited one paper here. We see that the difference can get quite large. So if we go down to, I don't know, 200 nanometer distance between the transistor and the N-well, the threshold shift is already, let's see, 40 millivolt, which is quite big. But still, if we keep a distance of 1 micro, we still have an offset. So in the layout, we have to take care that for matched structures, the environment is perfectly symmetrical. Another thing regarding layout is what I meant or said before is make use of unit devices. So imagine you have a current mirror with an input current and you want to have twice the output current. To do so, we would size the output transistor with twice the width compared to the input transistor, because then we have twice the current. If we look to the layout of this structure, you see that this transistor isn't the same like this one. So there are stress effects at the border, for instance, of the diffusion, which are different from this to this. So if we want to have a good matching or a low systematic offset, we are not going for this implementation. We are going for implementation like this. This is a design which is based on units. So instead of making the output transistor twice the width of the input transistor, we use 2 output transistors. So they are shorted, of course, but the structure in the layout is much more comparable to the input transistor. So by doing this, we are reducing the systematic offset, and this can be done quite easily. So as a designer, you have to draw your schematic like this so that the layout engineer can draw the layout also like this. This was about the systematic offset. More interesting, I would say, is the random offset. There is quite a famous paper about this random offset, especially on transistors by Marcel Pelgrom. It's quite old, but in general, it's still valid. What did he discover? I would say this is interesting and also helpful for us analog designers. So he looked into transistors which are placed in a so-called supersymmetrical environment and measured the threshold differences of those transistors. And out of this, he can derive the standard deviation of this threshold variation. And in this experiment, he discovered that this standard deviation depends on a technology constant, which is called AVT. This constant has the unit millivolt micrometer. So for instance, in a, 120 nanometer process, this is about 5 millivolt micrometer. Of course, this depends on the device type. So if it's a PMOS, an NMOS, thin or thick oxide, but to give you a rough number, it can be 5 millivolt micrometer. And this number is divided by the square root of the area of the transistor. So the width and the length. This means if we want to have a better matching between 2 transistors, we have to increase the area, either the width, the length, or both. Of course, with respect to analog circuits, we are typically not free to increase the area. So we have to keep the analog performance of our circuit in mind. And if we do this smartly, we can make it in a way that the analog performance will be better, but also the mismatch will be better. For this, I will have an example, of course. What you should also know that the so-called Pelgrom law, so from this paper, this isn't valid for modern technologies. So when we look to modern technologies, we see that this process constant depends on a lot of things. So it depends on the sizing again, so the length, the width, but also on the bias point. So it could be that this constant is different for transistors which operate in weak inversion compared to transistors which operate in strong inversion. But still, for first order approximation, this is still valid, and it's quite helpful because with this you can even do some hand calculations, so first order estimations in your circuit about the matching. One example on the smart sizing. Let's assume we have a current mirror. And I tried to draw an equivalent circuit here. So we have an input transistor connected to a diode, which is given as an ideal transistor. And we have an output transistor, which converts the gate source voltage back to a current, which is also ideal. But in between, we have an offset current source, which models the threshold mismatch between those 2 transistors. So this offset source has the standard deviation of the threshold mismatch of these two transistors. Looking to the circuit, we can define that the variation of the output current, so the sigma of the output current, is given by Gm times this offset voltage. We can, of course, write this down in an equation. So the output current variation is given by the threshold mismatch, the standard deviation, times Gm. And you already know that this parameter, but also Gm, depend on the sizing of the transistor. We can write this again here. So the sigma of the threshold mismatch is the process constant divided by the square root of the area, and Gm depends on the width divided by the length. So to have a small variation of the output current, of course, we want to increase the length and the width to reduce the sigma of the threshold variation. But when we look to the Gm, we want to increase L because we want to have a small Gm, but decrease the width to not increase Gm, because large Gm means large variation. So to summarize this, for the current mirror, we want to have a minimum Gm over ID to have a small variation of the output current. Or in other words, we want to have a narrow but long transistor. It's in the slides, but I'm not showing you today, but I mentioned it. For the differential pair, it's different. For the differential pair, for instance, we want to have a maximum Gm over ID. So it's opposite to the current mirror. And a good analog designer typically knows this. So by knowing this, he can already start with a good sizing before he or she went into simulation. For the current mirror, I have I would say, a practical example which I want to show to you. On a chip, we typically have so-called bias current banks. What is this? So we have several blocks on a chip, I don't know, an ADC, a regulator, an oscillator, and all of these sub-blocks require some bias current. We have somewhere a central biasing with a band gap and a voltage to current converter, which generates our bias current. And using a bias current bank, these bias currents are distributed to the individual blocks. Let's assume we did a design like this. So we have an input bias current going into the diode, and we have many output transistors which provide the bias currents for the individual blocks on the chip. If we do a sizing like this and do some statistical simulations, the details will follow, but for the moment, assume we are able to do this and we can estimate the maximum and the minimum current which is given by the threshold variation in production. If we do the sizing like this, we will have a typical bias current of 250 microamps, but due to the mismatch, we have to deal with a bias current variation of 310 microamps to 190 microamps. And of course, for a design, this is quite challenging because if you design an ADC, it has to work with this bias current as well as with the lower one. So this is not nice. How can we improve this? So we already know we want to have a low Gm over ID. So we are resizing these transistors. In this example, what I do is I keep the overall area constant. So this has an area of 4 micrometers squared, and this one also has 4 micrometers squared. But here I'm reducing the width by a factor of 10 compared to the original design, but increasing the length by a factor of 10. So we are significantly reducing the Gm. If we look again to the variation, we see it's much lower. So it's from 265 maybe to 235. So of course this is much better. And even by doing this, there is no drawback because the area is still the same, but the variation is much less. So a good designer would do a design like this, not something like this. Okay, so this brings me somehow to the end of the first part. I wanted to show you what variations, or give you an overview, so to say, what variations we have in the CMOS fabrication process. We saw that we have the global variations and the local variations. I tried to give you some ideas how we can make our designs robust against these variations. So for the global variations, we said we are using design concepts based on matching rather than on absolute parameters. And for the local variation, or for the mismatch, we are doing two things. We are reducing the systematic offset, but also with smart sizing, we are reducing the random offset, or the mismatch between those, between two devices or several devices. Of course, we are not doing this blindly. We need to somehow verify this already before going to production. So we want to ensure that all the measures we did to increase the robustness of our circuit will work out already in production. And to do so, we need to verify this in pre-silicon, meaning in our simulation environment. Since this variation in the fabrication process are a random process, so they follow a certain statistic, we have to use statistics in our verification as well. That's why the second part is called verification in statistical domain. Again, I have some subsections here. The main part will be on different simulation methods, but before I go into this, I want to introduce maybe not so well known way to plot statistical data. This is called a normal probability plot or a quantile plot. When you understand this, it's much more easy for you to follow the upcoming part about the different simulation methods. Let's start with the normal probability plot. Before I show you the normal probability plot, I show you another plot, the so-called histogram. This is typically quite well known. And if you understand how this is generated, it's also easier to understand how the quantile or the normal probability plot is generated. But I already said this now, that this type of plot is not well suited to show statistical data. You will see in a minute why. Still, how can we generate this type of plot? So assume we have a lot of data which is randomly distributed. To generate this type of plot, we sort this data by their value, so from smallest to largest, for instance. And then we introduce certain intervals or grouping. This means we define an interval size and group all these data points in these intervals. And afterwards, we count how many data points are in a certain interval. And this can be plotted. So for instance, you see this here. We have the data values on the x-axis and the count result on the y-axis. So in the interval, which is located at -1, for instance, we count approximately 915 values, for instance. So this is how we generate the histogram. The way the histogram looks like is, of course, given by the statistical function or the distribution which is behind. A very common distribution, which is very typical in analog chip design, is the normal distribution or the Gaussian distribution. This is the same, but with two different names. Such a distribution is very common for device parameters. So like the threshold voltage, for instance, this is distributed like this, but also circuit parameters. So if you do a simulation or a measurement of analog circuits like a band gap, many circuits, like the band gap voltage, for instance, have such a shape, meaning they are normally distributed. However, it is not always the case that the distribution looks like this. Sometimes we have so-called tails. This means that the distribution doesn't, so to say, stop like the histogram. It goes much further to the right than we want to have. And from this graph, we already see that the histogram is not so well suited to display such data, because typically we are interested in the tail, because tails indicate design problems. So in many cases, this is an indication that the design is not working as expected. So this is the important information, but in the histogram, it's quite small compared to the, let's say, mean value. This is quite big, but this is not so important. Usually we're interested in this. So the histogram is not well suited. To overcome this, we use the quantile plot or the normal probability plot. Of course, for the quantile plot, you need to know what a quantile is. What is a quantile? Simply speaking, the quantile is the x value, so the data value to a certain cumulative probability. What do I mean with this? If we plot the distribution function, as an example, again, the normal distribution, we see on the x-axis the data, and on the y-axis the probability. When we integrate the curve, we can plot the cumulative probability. So this is a result like this. The cumulative probability means, so for instance, when we look to the value 0, the probability that we get data values which are less than 0 is 50%. Or when we go up to 2, so to get data values which are less than 2, the probability is 98% approximately, for instance. So the graph can be read like this. When we speak about quantile, we go into the other direction. So we define a probability. So for instance, we want to know the data values for which the cumulative probability is 50%. So we go to the 50% and get a data value, in this example, of 0. Or we want to know the quantile, so the data value for a probability, a cumulative probability of 80%. We go to here and see what is the data value. So for 80%, we have 0.842, for instance. So the data value is the quantile for a given cumulative probability. And this can now be used to generate the so-called quantile plot. How are we generating this? Like for the histogram, we sort the data points by their value, so from smallest to largest. But instead of grouping and counting, we are estimating a theoretical quantile. So we are assuming that the data is normally distributed. This isn't necessary to be so, but we're just assuming it. And by doing so, we can calculate the probability if it would be normally distributed. This is quite easy. We take the number of the data point. So this is starting from the left. The fifth data point, we subtract 1.5 and divide it by the number of data points. So how many points we have. And then we calculate the quantile by using this function. So from the probability back to the quantile. The theoretical quantile, so to say. By doing this, we have now the data value, so the real quantile, and the theoretical quantile if it would be a normal distribution. And of course, this can be plotted. So on the x-axis, we have the data value, and on the y-axis, we have the theoretical quantile from the normal distribution. And of course, there's a close relation between the theoretical quantile and the probability. We saw this on the slide before. So we are typically plotting this value, but going into this graph, we can also get the probability. So in this graph, maybe I'll show you the next slide, we can exchange the y-axis, the quantile axis, with the probability axis. So the graph content doesn't change, we simply exchange the axis. Depending on the need, either one of them has an advantage or a disadvantage. When we look into this graph, I think there are two major benefits what we see. By the way, this is the same data what I showed you before in the histogram. What is clearly visible is that this curve has some bending. A bending always happens when the data does not follow a normal distribution anymore. Remember, we assumed the data is normally distributed. If this would be the case, we see a straight line. If this is not the case, the assumption was wrong, so to say, and we see some bending. And this bending is typically an indicator that our circuit has some operating modes which we do not want to have. So we see this here quite nicely. Another thing or another benefit of this type of graph is when we use the probability axis, we immediately see the yield value. So let's assume we have, this is some circuit parameter, and we have a specification for this, which is in this example 350 kilohertz. Then we look when the data points cross the limit line and look to the y-axis. So we see that 85 ppm are outside of this limit line. This means for this circuit, we would have a yield loss of 85%, 85 ppm, or a yield of 99.9915%. So from this graph, this can be read very easily. In comparison for the histogram, it's almost impossible to do so. You would have to count all the values which are right of the limit line or left of the limit line. So this is the way we show such data. And typically in modern simulators, this is now possible. So also if you use, for instance, spectra now switch to this format instead of using the histogram. Speaking of spectra, by knowing the graph format, I will show you now some verification methods which allows us to verify the robustness of our design. As said in the beginning, I want to start with the Monte Carlo simulation because this is quite well known. I would say every analog simulator implements this. I see a question in the chat. It states the y-axis is logarithmic. I have to say this is not true. This is not a logarithmic axis. This depends if you use quantile or probability. So the quantile is a linear axis, and the probability axis is scaled to the probability. So this is not linear, but also not logarithmic. This follows the Gaussian distribution. Coming back to the Monte Carlo simulation. So I said so many or almost all analog simulators implement this method. How is this working? So the variation of the different process parameters is typically quite well known. So foundries or companies like Infineon, they generate even wafers, so-called modeling wafers, which are used to generate the models what we use in analog design. So the variation of the individual parameters are quite well known. In simulation, we try now to emulate the behavior like we have in production. What the simulator does, it looks to the model files of the individual devices, and by the so-called sampling process, it selects different device parameters given to their probability in the model. A designer or a verification engineer has to specify the amount of samples. So for instance, 100, then the simulator randomly choose 100 sample sets, and these sample sets are then simulated. By doing this, we get the response of our circuit. So like it would behave when we go for mass production. The sampling process is of course very fast because it's just like a dice, so to say, but the simulation can take very long because we need to simulate a lot of sample sets to get a circuit response like this. Some word on the sampling. So generating the input data set. This is a two-step approach. First, we have some random number generator. This is like rolling dice. So we have random number generators which generate a uniform distribution. This means the probability for each data point is equal. There are different methods for this. There are simple random generators, but there are much better ones. They fall into the class of low discrepancy sequences. Like here, this is a Halton sequence, which is used by Spectre, for instance. So by this, we get a lot of random variables. They are uniformly distributed. So if you plot the uniform distribution in the quantile plot, it looks like this. And of course, I said, so our parameters are not uniformly distributed, or typically not, luckily. We have different distributions, and we have to somehow map this to the real distribution function. This can be done easily by mathematics. I will not show you the details on this, but maybe you can remember the name. This is called inverse sampling. By this method, we can generate any distribution function out of any other distribution function or the uniform distribution function. So what the simulator does, it generates the random numbers, then it looks into the model file. So for instance, this is a model file from which is understandable by the Spectre simulator. Here is the threshold voltage. This is given by a Gaussian distribution and some standard deviation. By knowing this, the simulator generates the input samples which we need for simulation. So to summarize this, the Monte Carlo simulation is doing the following. First, we generate the samples, so we are rolling dice, then calculating the individual device parameters, so threshold voltage, resistance, and so on. Then we go for simulation. And when the simulation is done, we are plotting our results in a normal probability plot or the quantile plot to see how our circuit will react to the variation in the process. So you can say this one is the processing steps, and this is what we will get when we measure our chips. Also on the Monte Carlo simulation, I prepared a small example to do so. I invented or designed a circuit. This circuit has no practical use. It's just be done to be an illustrative example also for the limitations of Monte Carlo. I gave the circuit a name. It's called Björn's problem. This is just that it's easier to refer. So every time when I say Björn, I mean this circuit. What is the idea of this circuit? In general, we have a simple current mirror, so one input current and two output current. And the output currents are transformed into a voltage using resistors. It's done like this, that the resistors are ideal, so they do not have any variation, but the transistors are, so to say, real transistors, which undergo a certain variation in the processing steps. So we have two output voltages, and there's also a comparator. And the comparator selects which output voltage actually goes to the output. And it's done like this, that in the most cases, so almost every time, the output is Vout1. But in some cases, and this is the case when this voltage is larger than this voltage, the output is Vout2, but this is a rare event. So with this circuit, we can emulate two operating modes of an analog design, which can happen. So we have a normal mode, so to say, where we have Vout2, but we have also, in some cases, Vout2, which is an unwanted behavior. Let's make an assumption about the simulation time. So let's assume that when we do 100 Monte Carlo runs, this takes about 1 hour. Of course, for this circuit, it might be too pessimistic, but for a typical analog design, I would say this is a good assumption, and we use this for illustration in this example. The purpose of this example is now to show you what we can do with Monte Carlo, but also what the limitations are. So let's assume we do a Monte Carlo simulation with 100 runs. On the left side, you see the three transistors, and there are threshold voltages in green, which are taken by the simulator. So there are 100 green dots. Of course, most of the samples are around 0 because this is the highest probability for the values to get. If we simulate this, by the way, this takes 1 hour because we have 100 runs, we get this output response. On the first look, this looks quite nice. So we have a straight line, and by seeing this, I would say nothing to worry. Already here be warned, what sometimes happens is that this simulation result is extrapolated. So by fitting a straight line, it could be theoretically estimated what is the value of the output for up to, I don't know, 5 sigma. So people say, let's take the mean and add, I don't know, 5 sigma to it, and let's see what is the value. Never do this, because you will never know how the circuit will behave when you do more Monte Carlo simulations. What happens for this circuit, I can show you. So let's say we increase the number of runs to 500. So we are already simulating now 5 times. We see most of the samples are still at the center, but of course we get more samples in the outside. Looking to the output, yeah, it's still nice. We could say, yeah, here starts some bending, but I would say it's not yet clear. So let's increase the number of runs even further. So we are now at 1K, already 10 hours. If you compare the output, if I switch back and forth, there's not so much change. So nice straight line, maybe some bending here. Let's go for 5K runs. So it's already 50 hours, so more than 2 days. And by seeing this, we see, oh no, our circuit has an unwanted tail. So there is clearly a second operating mode. Of course, we knew that because I told you about this comparator, but usually we do not know. So to recover this problem, we need, in this example, 50-hour simulation time of 5K Monte Carlo runs. Of course, we can increase the number of runs even further. And I think I did it up to 21 days. So 500 hours. Then we get our samples distributed up to 4 sigma, and we see the final result. So we see the tail. We also see that we hit the limit at approximately, I don't know, 0.2%. So this circuit would cause a significant yield loss. But to simulate this, we need 21 days. Typically, I would say this is not feasible for a design. So I would summarize that Monte Carlo simulation is not suited if we want to simulate for high yield values. Here again, the comparison. So for 5-hour simulation, everything looks nice. But if we go to 21 days, like in this example, it doesn't look so nice. Still, Monte Carlo is a useful tool when it comes to optimizing a circuit. What do I mean with that? So when we look to the center of the distribution, we have some standard deviation here, which can be calculated. And by optimizing, I mean we want to rotate this. So by means reducing the variation itself. So typically we are not able to find such tails, but what we can do is we can reduce the dominant part of the variation. How can we do that? So for instance, there is a so-called correlation analysis or sensitivity analysis when we run Monte Carlo simulation. Correlation is we plot our output, so V out, for instance, versus an input sample. So for instance, the threshold of transistor M1. What we see here is that there's a nice correlation between the threshold of M1 and V out. So the larger the threshold of M1, the larger V out, which means if we are able to reduce the variation of the threshold of M1, we can reduce the variation of V out. And we already know this is a current mirror. So let's reduce GM and we get a better result here. What we also see in correlation, so there is the transistor M2, there's almost no correlation. So if we are changing this transistor, it will not benefit us when we want to reduce V out. So Monte Carlo can be used for this, but it typically cannot be used to ensure a high yield. To do so, there are more innovative methods, which I'm going to present now. And these methods are summarized in the topic of high sigma verification. High sigma means we want to simulate up to very high sigma values or very low probability values. Let me just check the clock. Yeah. Before I show you some method, I want to do a short revision on sampling. I do this because the different methods I'm going to show, they distinguish in different sampling methods. So it's good to know what sampling actually is. By sampling, I mean calculating the input variables of our simulation. So doing the dicing to get the different threshold voltages, for instance. So this is not simulating, this is just calculating the values which we are going to simulate in our simulation environment. And contrary to this, we have the response, it's plotted on the right side. So this is how our circuit is responding in simulation to the sampled values. And of course, in the response, we can define a failure region. This is, or a tail region. This is the region where our circuit is going to fail, or where we have a violation of the specification. When we speak of samples, we can introduce another graph. This is a sample space. If we just have two samples, so assuming we have just two transistors, this is a two-dimensional plot, which can be easily done. If you have more than two, it gets complicated. How can we do this? So we have on the y-axis one threshold and on the x-axis the other threshold, and we can find some dots which represent the actual sample values. And inside of this graph, if we know, and this is the tricky part, we can also draw the failure region, meaning which sample values cause the circuit to fail. So for instance, we have here two values which are out of spec, and these are caused if the threshold voltage of the two transistors is like this or like this. So what is the basic concept for high sigma verification? It's still very similar to the classical Monte Carlo. So you see this in the box. This is the Monte Carlo approach, which I showed before. The difference is we optimize the sample generation. So what we're going to do is we generate some samples, do only some simulations, and depending on the outcome of the simulation, we are modifying the sample generation. So the idea is we are only simulating samples which actually fall into the failure region. Sounds trivial. It isn't, because we do not know a priori which samples are going to fail or which are not going to fail. And of course, depending on the sample generation, so on this process, there are better methods or methods which are not so good. There is a nice paper which provides an overview on the different methods which are available. So there's a long list in this paper. Note this is still not complete, but I would say most important methods are summarized in this paper. Out of this, I want to show you two methods. I'm going to show you this because they are available in commercial products. The first one I'm going to show you is the scaled sigma sampling. This is implemented in Cadence Spectre. So if you're a Spectre user, you have access to this method. The second method I'm going to show you is the so-called statistical blockage. This is implemented in a tool called Variation Designer. This tool was originally distributed by a company called Solido, but this company is bought by Mentor. So it's now Mentor. And this can be, of course, also used. This Variation Designer provides several verification methods. Sorry. The one I'm going to show you today is the high sigma Monte Carlo, which implements the statistical blockage. But let's start with the spectrum method, which is called scaled sigma sampling. The idea of this method is we define a model for the failure rate. The failure rate is the yield. And the model is done like this. We have three constants or model parameters, alpha, beta, and gamma. And we have a scaling factor S. This scaling factor is a factor which we use to scale the sigma of our input variables. So means we have a standard deviation for the threshold, given, I don't know, for instance, with 5 millivolt, and we scale this with S. So if S is 2, we get 10 millivolt standard deviation. And if S is 3, we get 50 millivolt standard deviation. And the idea is now, by simulation, we want to solve for this model parameter, alpha, beta, and gamma. And if we have this, we can calculate the failure rate or the yield value. So in the simulator, we start with S is 1, look to the failure rate. Then we start with S is 2, look to the failure rate. And repeat this experiment until we are able to solve this equation and calculate the yield value. Personally, I would say this method has a very big drawback. The drawback is we get a yield value, but we do not get any distribution function. So I don't know, after the simulation, we know our circuit has a yield of 99.9996%, but we are not getting any distribution, so we are not seeing if there is any tail or everything is behaving like expected. So this is not so nice in my point of view, but still, of course, if you have access to it, you can try it out and see how your circuit will behave during production. A nicer method is the statistical blockage. What is the idea behind this? here we are generating, but not simulating, a lot of samples. And you will see these are 10 giga samples, for instance, or even more. And then we are trying to classify these samples into two categories. We have samples which are going to fail, which are going to lead into the failure region, so which cause our circuit to fail. And we have samples which are leading to results out of the failure region. And by this classification, we do this is called blocking now. So we block all samples which are not falling into the failure region. So we are only simulating the samples which fall into the failure region. The crux now is, or the complex task now is to find a classifier which tells us in advance which samples we need to simulate and which samples are not so important for us. In this high sigma Monte Carlo tool from Solido, they have the idea of a so-called ordering model for the classifier. The ordering model is they try to predict the order of the samples in the output response. And of course, this is closely related to the probability, because the first sample is the one which has the lowest probability, and the last one has a much higher probability. How they are generating this model is proprietary, and unfortunately, we do not know many details on this. There is a white paper on this method, and it just tells that they leverage machine learning. So I don't know how this works, but I can say I tried it a lot, and yeah, it's quite robust. So what they are doing is they're generating a lot of Monte Carlo samples, take an initial amount of these samples, and they simulate this. Having this simulation result, they use the machine learning to generate the ordering model. And when they have the ordering model, only samples which fall into the tail area or the failure region are simulated. I can show you this on the Björn example again. So if we use this simulation method on the Björn circuit, it's done like this. So we define we want to estimate up to 6 sigma, which is quite far away from the mean value. To do so, the tool generates 10 gigasamples or even more. Out of these 10 gigasamples, it takes 2K samples, which are simulated to generate the model. If we look to the sample space, these are these light green dots. They are nicely distributed over the whole sample space. So they are used to generate the model. When the model is done, another 2K samples for the upper side and another 2K samples for the lower side are selected. And if we look to the sample space, they are quite centered in this area and this area. So by the ordering model, it could be predicted that we need samples in this area, but not in this area, because samples in this area will not fall into the tail region. And if we look to the simulation result, so we see the lower side and the upper side, this fits very well to the Monte Carlo simulation. So by this, the tails can be estimated quite nicely. In comparison, also in the sample space, I tried to plot the samples from the Monte Carlo. We see the 50K samples, which are located at the very center in this space. So there are hardly any samples which are in the tail area. That's why we don't see any dots for the Monte Carlo outside here. It's clear because the probability to get such a value is quite low. But in high sigma Monte Carlo, this is possible. To summarize this a little bit, so the high sigma verification method, they provide a sampling method which allows us to accurately estimate a tail of a distribution or the failure rate. I showed you two different methods, one from Cadence Spectre, which implemented the scaled sigma sampling. This allows us to calculate the failure rate or the yield, but not any distribution function. And contrary to this, I showed you the high sigma Monte Carlo, which implements the so-called statistical blockage, which allows us to simulate really the tails of the distribution. So we really get results up to 6 sigma. But, and here comes now the big but, is this what we need in analog design? And I would say not really. Why is this the case? First, it's not so important for us to predict an exact yield value. And I would say it's even not possible, because all of the simulation methods require very accurate models, especially if we go up to very high sigma models, sigma results. And of course, this is not possible to have such accurate models. So the exact yield value will anyhow be wrong. And something which I didn't mention so far is we were not speaking about different conditions. So of course, an analog circuit has to operate at a large temperature range or a large supply range. And it is not clear in advance which temperature shows the worst performance. And our high sigma verification method, we just did at one condition. So maybe typical temperature and typical supply, but it could be that hot is much worse. So I would say this is not really what we want. What we want to have is, we want to prove that our circuit will work up to 4, better 5 sigma, but 6 sigma is maybe a little bit too much at all given conditions. So at all temperatures, all supply voltages, and all bias conditions, for instance. For this, of course, there are also commercial products, one again from Mentor Solido, or there's another one from Moneda. Both solutions are, again, proprietary. It's really hard to tell how they work internally. And they would say for research and academic, but also for companies like Infineon, this is not a nice solution. So at least from my point of view, in this area, this is still a big research topic. And of course, if you're interested in this and want to do some research in this area, please contact me. I think this, especially in the future, this will get quite important. Because in the end, we want to verify that our designs will work already before we go into production. And this is what we need to do this. And I would say there are not so much products available. About the conditions, I want to stress this a little bit more. So let's assume we have a circuit and we simulate this. So no statistical simulations. Let's say a DC simulation at 3 different temperatures. When we do this, we get for this circuit 3 different output voltages. We have the output at cold, at room temperature, and at hot. When we look to this, we see the hot value is closer to the limit. So when we use a high sigma verification method, we would use the hot one because it's already close. So let's see how this behaves. But what can happen is, and I did now simulate all 3 temperatures, is that for cold and for hot, the circuit has a nice normal distribution and it behaves quite nicely. But at room temperature, there seems to be a problem. So there is a tail. This means that, or this results in a result that the room temperature is much more close to the limit compared to the hot temperature. So you see the dots change their place. So for this circuit, we would need to do our high sigma verification at room temperature, but not at hot. But of course, we cannot tell this in advance. So we need some method which finds out which condition needs to be investigated. And I said there is a commercial tool for this. I want to show this briefly. This is again from Solido Mentor. This is called PVT-MC. I call this next step in high sigma verification because actually it does what we need. It automatically detects the worst case condition. So at least in theory, it finds out which temperature, which supply, which bias condition is the worst case. And only in this worst case, the high sigma verification is done. But the high sigma verification is not to extremely high sigma values. It's up to 4.5 sigma, maybe 5 sigma, which is typically sufficient for analog designs. As said, details on the implementation are proprietary. What is published is how the worst case condition is detected, or on a high level published, so to say. The idea is they introduce so-called ordinal classes. Ordinal class means we have several conditions which lead to a similar statistical response. So when I go back, when we look to this graph, the cold and the hot would be from the same ordinal class because the statistical response is quite similar. So we have a normal distribution. Of course, there's a different mean value, maybe also a different standard deviation, but in general, it's similar. The room temperature is different. So this would be from a different ordinal class. The ordinal class is estimated by using the same ordering model idea what has been used for high sigma Monte Carlo. So if the ordering model is valid for several conditions, or the same ordering model, they fall into the same ordinal class. And for the estimation of the distribution function, the paper just states it's an enhancement of the sampling and classification algorithm compared to high sigma Monte Carlo. So we are really lacking of the details here. What is quite impressive, at least from my perspective, when we look to the simulation results. Again, I used the Bjorn circuit. Now I'm using 3 temperatures, and it's defined like this, that the tail, so this comparator, only operates at minus 50 degree. 50 degree and 150 degree are fine. With the light dots in the background somehow, I did the Monte Carlo simulation with 50K runs at each temperature. This is the golden result, so to say. So we have hot and room temperature, which is behaving quite nice, and we have cold with the tail. If we simulate this circuit in PVT-MC, the tool requires only 330 runs, which is really a low value, I would say. At hot and at room temperature, only 15 runs are done. So these are just dots to estimate or to roughly estimate the distribution. As this is not the worst case, the simulation runs are reduced to a minimum. The worst case condition, which is minus 50 degree, is simulated with 300 runs. This is also quite a low value because when you look to this, especially also to high sigma values, 4.5 sigma, the accuracy is still quite high. So from my perspective, this is what we need in analog design. This tells us the worst case condition, and this tells us how our circuit will behave during production and also in the field. I promised you in the beginning, I will wake you up when I come to the takeaway slide, because I guess this is the most important one. So wake up, everybody. I'm at the takeaway. With this slide, I want to summarize the whole presentation today. In the beginning, I tried to show you that the fabrication process, the CMOS fabrication process, suffers from certain variations. Yes, there are some monitoring structures on a wafer, the PCM structures, but these structures do not have a focus on analog parameters. So we analog designers have the task to make our circuits robust against these variations. I showed you some methods, how we can improve for global variations, but also for local variations. And of course, it's already nice or even mandatory to ensure that our design, which we did, hopefully robust, is going to work in production or after production. So we want to do some verification here. These are statistical simulations. I showed you the well-known Monte Carlo technique, the limitations for it, and that we need some other methods, more innovative methods, which allows us to peak in the high sigma regime. Here I showed you the high sigma verification methods, namely two of them, one which is implemented in cadence spectra and another one which is implemented in high sigma Monte Carlo from Solido. We learned that the high sigma verification methods are maybe not what we really need in analog design, because we do not want to predict the high yield value. Even it's impossible because of inaccuracies in the model, for instance. And there is the big topic of conditions. So the statistical response of our circuit might change at different temperatures, different supply voltages, and so on. For this, I showed you one solution, which is also from Solido. This is called PVT-MC. But still, I would say there are only a few solutions which are present, and they are not, so they are proprietary. So from my point of view, this is really a nice and big research topic. Coming to the end, I said in the beginning, there is going to be a quiz. If you remember, I introduced you the 3 answers to unwanted questions an analog designer has to know. And the question now is, what are the answers for an analog designer who knows statistical verification? I guess you paid attention or had a close look. I would say the answer is easy. Of course, the 3 answers stay the same because we are still analog designers, but we learn statistics. So we can add with a probability of 95%. So we are saying, I don't know, with a probability of 95%. With this, I'm coming now really to the end.